Good morning and welcome you all to the NPTEL course Advanced Distribution System Analysis and Operation, and we are continuing at the module 2, which is DER Integrated Distribution Network Modeling. So, we will continue with the modeling and operation of DER's part. In the last class, we have seen the modeling and operation of PV panels or solar power generation. Today, we will continue with the wind power generation. So, wind power generations, what it does? It converts the kinetic energy of the wind into the electrical energy that we can use with the help of wind turbines. So, first the wind blows and hit the turbine blade, then the turbine blade will start rotating, then it will rotate a shaft that is connected to a shaft, the blades. That shaft is now going to a gearbox. Now, what is the purpose of this gearbox? Because generally you have seen or noticed that the wind blades are very big. So, the rotational speed of that wind blade or the shaft is very slow. So, with that slow RPM, it may be let us say 10 rotation per minute or maybe 20 rotation per minute. With that you never can generate electricity. So, there has to be some mechanical arrangements that will amplify that speed to the actual synchronous level speed for the generators. So, that is done by your gearbox. Then you have generators to generate the electricity. To connect them with the grid, you have power electronics converters and transformers, and then at the end you have your AC grid. So, that is how the wind power plants are generally connected with the distribution network or power network. So, first we will see how the wind power generation is done. First, the kinetic energy of a mass m of air which is blowing at a velocity of v is carrying a kinetic energy of half mv square, that we know. Okay. Now, if that amount of wind that is blows through the area that is actually the blade area or the swept area, that means how much area blade is covering while the rotation, that is called the swept area. If it is blowing through that and your air density is rho, that is close to your 1 kg per meter cube, and then the total amount of volume of air blows to the swept area is A multiplied with V. Then your mass flow rate is dm by dt, which is rho a v. Okay. So, the wind power generated, that will be your change in energy with time, change in energy with change in time. So, if you do that d kinetic energy by dt, then you have half of dm by dt into v square, and if we put that value here, we will get the total rated capacity of an wind power plant. That is the rated, that is not the actual power generation. That is the maximum amount of power you can generate if your wind is blowing at a v speed. So, you can see that your actual power generation or the rated power generation, that is proportional to cube times of your wind velocity. That means, if you have a small increase in the wind speed, then you have a large increase in your power output. So, that is the main methodology of the wind power generation. So, if you add the efficiency term, because I told this is the maximum power you can get, but obviously you will not get maximum power because you have so many gearbox, you have generators, you have your blades, everything is a mechanical device. So, obviously they are certain losses, they are certain efficiency level. So, if you put that term, then it will become the expression half Cp rho AVQ kilowatt, and the value of Cp is very less, that is 0.25 to 0.45. That means, what actually amount of power you can harness from your wind power generation, maximum 45% of that actually you will get from your wind turbine. So, that is the mechanical limitation you can say of the wind turbine arrangements. Now, is it possible that whatever wind speed you will get and you will get power always? That means, let us say your wind is blowing at 1 meter per second, will you get wind energy? Or let us say you have a hurricane, that means it is blowing at 100 meter per second. hurricane or cyclone you have. So, will you get power at both the time? No, because if your wind speed is very low, at that time how much power you are generating, that is lost in your mechanical devices. So, that cannot come up or cannot recover the amount of friction loss you have at your mechanical arrangement. So, you will not get any power output from your, or close to zero power from your wind turbines. Now, again if your wind speed is very high, then what will happen? Let us say we have arrangement of a gearbox which is making this 15 rpm to 1500 rpm. That means you have 100 times more amplification of your speed. Now, if your wind blows at 100 meter per second, then this 15 will, let us say, go up to 150. Okay. Then with this arrangement again it will go to 100 times, then it will become 15,000 rpm. So, that your generator cannot handle, and that may even cause damage to your wind turbine. So, for that time you have a braking system or a blade pitch control that will disconnect your wind turbine or wind blades from your generator circuit. So, very high wind speed as well you will not get your power generation. So, depending upon that, you have 3 reference volt speed values for wind power generation. First is called cut-in speed. Below that speed you will never get power generation. So, that is around 3 to 4 meter per second. Then you have a rated wind speed, that means at that wind speed value or wind speed range, your power generation will be at the rated or the maximum value. Okay. Then you have a cutout wind speed, that means above that speed level, wind speed level, again your braking system or your control system will operate and you will get 0 output power. So, if you see the power versus speed curve, wind speed curve, you can see after the cut in you will get the linearly, mostly linearly increasing output power. Then at a certain range from around 12 meter per second to 15 or 20 meter per second, you will get constant amount or maximum amount of power, and then after Mach 20 or 25 meter per second, you suddenly you will see a sharp drop in your wind power generation and it will come to 0 value. So, the same thing we have represented here in the mathematical form, that if it is lesser than cut in speed or more than cut out speed, then your output power is 0. If it is within the range of cut in to the rated, then it will linearly increase or linear variation, and if it is within the rated and the cutout, then you will have rated amount of power. So, how will you integrate now this wind turbine to the AC grid? You have mostly we use two kinds of arrangements. One uses permanent magnet synchronous generator, where the PMSG is connected with your wind blades, but the synchronous speed of that PMSG setup may not be equal with the or synchronized with the frequency of your grid side. So, if you have a frequency imbalance, then you will get a short circuit current and your grid will collapse. So, for that we have a machine side converter like an AC to DC converter, we convert it to the DC, then from DC to AC, and then we connect it with the grid. So, this is the PMSG setup. Another setup that is called a DFIG setup, that is a doubly fed induction generator setup, where the stator output of the DFIG is in synchronism with the grid, and you will get supply in the 50 or 60 hertz power output. The excess amount of power you will take from the rotor, and you are obviously, if it is an induction machine, you know the induction machine generator, the speed is more than its synchronous speed, that means it is running at a super synchronous level. So, at that time the rotor frequency is not equal to your grid frequency. So, at that time what we use? We convert the rotor power first from AC to DC by using a rotor side converter, and then converting again from DC to AC, synchronizing with the grid frequency and grid voltage, we connect it with the grid side converter. So, this is the overall connection diagram for turbine with the AC grid. Now, how we will get reactive power support from this wind turbine setup? if you have a PMSG setup, then you have one converter and an inverter. It is same like your PV inverters, what we told, that you will get your reactive power supply from this grid side converter or grid side inverter. You will run that with a lagging or leading power factor, and depending upon that you will get your reactive power support. But for DFIG setup, the lower rotor circuit, the reactive power support concept is same. That means you have a grid side converter or grid side inverter. Similarly, you will get your lagging with the lagging or leading power factor capability, you will get your reactive power support. But for the DFIG itself, that machine also can give you reactive power support and directly from its stator to the grid. And that is done by controlling the excitation of the system or the machine. If your network is, if your DFIG system is over excited, at that time it can operate as a capacitive element and can supply reactive power to the grid. Similarly, if it is at the under excited state, at that time it can act as an inductor and can absorb reactive power from the circuit. So, that means your DFIG setup itself can operate as an capacitor or the capacitive element or represent as an inductive element, and keeping the reactive power output within its capacity, that means the Q minimum to Q max value. With this, we will end the DERs for the generation, and now we will go to the storing equipment or energy storage one, which will store energy for giving you the supply whenever you need it, and it will store energy or it will charge itself when you have a excess amount of electrical energy available in your circuit. So, electrical energy storage refers to a process of converting electrical energy from a power network into a form that can be stored for converting back to electrical energy when needed. What does it mean? When you have an excess energy, you stored that energy in a different form and then again convert it back to the electrical energy when you were needing it. Okay. So, that is mostly used to mitigate the intermittency level of the renewable energy generation, because your solar and the wind, they are highly intermittent. So, to reduce that intermittent level, you can use the storage technology. That means, let us say your solar power generation is very high, but your load is not that much very high. So, that excess or the surplus solar energy, other than operating at the deviated from your MPPT level, that means you are losing your cheaper energy or your good energy, you can store that energy to your storage. Similarly, whenever your solar power generation is less, at that time you can, if your load is very high, at that time you can discharge the stored energy from your storage and can send it back to the circuit to meet the load. So, that is how the intermittency or the uncertainty involved with the renewable energy generation is mostly mitigated. So, if you see from this diagram that if this is your load profile, then if you can at the off peak time, generally at the off peak time we have less electricity cost. You can store or you can charge your energy storage, and at the peak time when your electricity cost is high, you can discharge your energy storage. So, if you do that, then what will happen? Your load profile will become, the net load profile will become flat. Similarly, if you take power from a dispatchable power generation, let us say it is a thermal power generation or a diesel generator. So, other than multiple times ramping it up or ramping it down depending upon the load profile, so if you do this charging one, so that means that will make your elevate your off peak or do a valley filling kind of work at the off peak time. Similarly, if you discharge at the peak time, that means that will cater the peak and you need not to ramp up your generator. So, that means you can run your power generation at a constant value. So, first benefit, you will get a constant or a almost flat voltage load profile, and the second, you will have a constant generation other than stressing your dispatchable generator by doing multiple times ramp up and ramp down orders. So, these are the type of energy storage generally used. Depending upon, in at which form you are storing that electrical energy. You can store it as a mechanical energy, you can store it as itself as an electrical energy, as a chemical energy, or as a thermal energy. Depending upon that, you can store as a potential energy for mechanical, similarly kinetic energy. Electrical energy you can store as a supercapacitor or superconducting magnet. Electrochemical, the famous battery or flow batteries. In chemical, fuel cell, metal air, and thermal, you have low temperature thermal storage or high temperature thermal storage. For potential, you can store it as a pump storage hydro, which is a very high or huge amount of energy storage facility, or you can have compressed air energy storage, or as a kinetic energy, you can store it as a flywheel. There is a device to store electrical energy as a kinetic energy. First, we will see how the pump storage hydro works. Generally, in case of pump storage hydro, that is built in the hilly region, where you have two reservoirs, one is the upper reservoir and another is a lower reservoir placed at the hill. That means one at the down at the hill, one is at the up of the hill. So, it operates when, let us say you have a renewable power generation available. At that time, you will pump the water from the lower reservoir to the upper reservoir. And similarly, when you need that water or you need that electricity, at that time you discharge the upper reservoir water through the turbine to the lower reservoir, and that is how the hydro power generation is done. So, then you will get your electricity and then you can use it, and again you just pump it back at the low peak time or low price time. Okay. So, that is how the operation of the pump storage hydro is done. But what are the drawbacks of it? First thing is that you need a proper geography to build this pump storage hydro facility. You cannot build it at the plains. That means you cannot build it anywhere you want. You have to proper geographical sites for building this upper and the lower reservoir. Second thing, always building reservoir dams take a huge amount of capital investment. Then we have few running projects in India where mostly we have currently 4.7 gigawatt of operational pump storage hydro and 2.8 gigawatt is under construction. Central Electricity Authority of India, they have estimated that the potential of pump storage hydro that is run on river mostly, that will have dam on the river and will generate, but the pumping back is very nominal. Okay. So, the run on river pump storage capacity we have of 103 gigawatt, and we have total 8 run on river pump storage hydros and 3 are on the building stage. These are the two big pump storage hydro facilities we have in India. One is Kadana pump storage, that is on the Mahi river at Gujarat, almost 240 megawatt of capacity, and the largest one is the Sardar Sarovar pump storage hydro, which is on the Narmada river at Gujarat, and it is almost 1.2 gigawatt of capacity. So, you can see how much huge amount of energy at the gigawatt level you can store with the help of pump storage hydro. But the problem is that you have to build this huge dam to store that much amount of energy as a kinetic energy. Then the next type of energy storage, which is called a compressed air energy storage, where you have a motor to compress air underground, stored as a underground and then release whenever you need it. So, a multi-stage compressor with cooling system enhances the efficiency and reduce the moisture, because if your air has a moisture, then that will deteriorate the life expectancy of any mechanical devices, if it is a turbine or anything else. The turbine system include both high and low pressure turbines. Then you have an underground structure like rock caverns or salt caverns or porous reservoirs to store the high pressure air there, and then you have a fuel or heat exchange mechanism to give the air back to the turbine to get the generation or the electric power generation. So, this is the operation of compressed air energy storage, where at the low demand time energy stored as a compressed air at almost 4 to 8 megapascal level of pressure at the underground, and then you have stored that energy as a high kinetic pressure energy. You will store it and then you will release it when you need it. That means you will expand it to the high pressure turbine, then you send it to the compressed air to that turbine level, that will help it to rotate, and that rotation will give you the shaft power, and that shaft power will go to the generator, and that generator will then feed power to the grid. So, in India we have a very limited facility of compressed air energy storage. Almost all only 1.05% of Indian land is actually suitable to build compressed air energy storage. Few pilot projects are running in Andhra and they are expected to generate 300 megawatt by 2030. But the major problem or the drawbacks for building this CAES is that first you have to have an underground chamber to store that air in a high pressure. So, that is difficult, because mostly that is used that whenever coal fields, like you take out all the coals and you have a empty coal mine. So, at there normally we build it, but the favorable geography for this are not very popular in our country. The most promising energy storage technology is the battery storage technology, where the energy is stored as an electrochemical energy. That means it has an anode as an cathode and electrolyte as a separator arrangement to flow of the ion inside the battery segment. Then you have a collector to do the electron transfer. That means whenever you have a charging, then electron will flow inside the battery, and whenever you need to discharge, then it will, the power current will go out from the battery. So, the operation is, during the charging operation, electrical energy drives the electron from the cathode to anode. Anode means it is a negative potential. So, the electrons will go there and they will store. Okay. Then at the discharging time, your chemical energy converts the electrical energy, that means it will release the electrons and that will go from anode to cathode side, and that will then go back to the main grid. So, these are the different kinds of battery technologies. Very popular, lithium ion, which is mainly used for electric vehicles and other power electronics devices. The life cycle is almost 1000 to 3000 cycles it can cover. So, that is why its life expectancy is very high. It is a very fast operating and high energy density and lightweight battery. So, that is why it is favorable or very popular to use an electric vehicle battery. Then you have lead acid batteries, which is very low cost, and life cycle is also very less. Obviously, if the life cycle is less, that means it is a low cost material. Operation is also slow and moderate. It is a low energy density and a very heavy one. So, lead acid is not very popular nowadays. Then you have nickel cadmium, where it is a moderate cost. Its life cycle is also moderate in between lead acid and lithium ion, but it is a tolerant to overcharging. That is the main benefit of using nickel cadmium. So, that is why it is mostly used for portable power tools and photography equipment. So, now we will go how this battery is operated. First thing is the charging thing. So, whenever you have an extra power available from your external source, that means you have a extra renewable power generation, or it may possible that your energy price is very low. So, at that time you will take power from the power networks and you will do the charging operation. So, if the charging operation is happening, then obviously your energy level of the battery will increase. Okay. The reverse thing will happen when you go with the discharging operation. That means you are supplying the power to your grid and that will reduce the energy level of the battery. Okay. So, if you catch these two things, you can mathematically model that as your energy level for the next time period will be current time period energy level plus how much power you are charging with the efficiency obviously, then how much power you are discharging. So, net of that if you take, then that will be your total energy level of the current. So, energy discharge and energy charge, net of that with the current scenario will give how much energy level you are going to get at the next time interval. But this charging and the discharging operation you cannot do it simultaneously, because you have only two ports, right. Either it can charge or it can discharge. Now, both the operations simultaneously is not possible. So, to model that one, you can use a binary variable 0 and 1, which will give that whether your battery is in a charging mode or it is discharging mode. How? Let us say first thing is that your charging and discharging, obviously that will be within a certain limit. You cannot infinitely charge or infinitely discharge like the power output. So, let us say your mu b, this binary variable is 1. If it is 1, then this will become 1. So, you are activating your charging operation. But if it is a 1, then your discharging operation will become 0, because PBCH is 0, less than equals to 0, greater than equals to 0. That means it can take only one value, that is 0. That means you are deactivating your discharging operation. The reverse thing is possible when you will take 0 operation, or you will take the binary variable 0. So, at that time you are deactivating the charging operation, but activating the discharging operation. So, that is how the simultaneous charging discharging is avoided whenever you model the battery in a mathematical or analytical time frame. Then your energy level, obviously that is also needs to be bounded, because your battery capacity is limited and you cannot discharge your battery after a certain time, that you cannot make it a 0 energy level, that will reduce the life expectancy of the battery. So, the battery energy always must be in the minimum to the maximum energy limit, and that is mostly from the 20 to 30% of the battery rated energy to the 90 to 95% of the rated energy level. So, again battery is a DC powered equipment, that means you will only get unidirectional power flow from the battery. So, you get DC electricity. So, connect that with the AC grid, you need a mediator, and that is done by a bidirectional AC DC converter. Now, why we want bidirectional? We will come to that. So, in contrast with the PV inverter, where it is mostly an unidirectional inverter, where the active power is only fed to the network, but in battery you will have active power go from the both the side. That means, active power can be go out of the battery or it can go inside the battery. So, your inverter topology must be a bidirectional, and same for your reactive power. It can supply reactive power or it can also absorb reactive power. So, depending upon that, your connection can be of two ways. First type of connection, that is called the DC coupled configuration. What you will do? You will connect the battery at the DC port where your PV inverter is already connected. So, after the PV inverter you have a DC-DC boost converter to boost the voltage, and after a battery you have a bidirectional DC-DC converter that will use the charging and the discharging operation, and both are connected at the DC link, and the net amount of active power you will get at the DC link. Then it will be converted to the AC power with the help of a bidirectional DC AC converter, which is responsible to give the active, net active and your required reactive power supply to the AC loads. So, that is the operation or the connection for a DC coupled configuration. The second configuration, that is the AC coupled configuration, where you will connect the battery at the PCC or the point of common coupling point of the battery. Okay. So, how you can do it? Similar PV panel will be connected like that, what you have seen before as well, a DC-DC converter and a PV inverter, what you have done in the PV classes. But for battery we have a separate arrangement, one bidirectional DC-DC converter and also one bidirectional DC-AC converter. So, other than having two inverters, now you have one inverter, now you have two inverters for AC coupled operation, and that connection you will have at the PCC. So, this inverter unidirectional one will only give only active power supply, but reactive power it can regulate at both the side, but your battery inverters that can manage the active and reactive power both at both the sides. So, previously your solar inverter capability curve is operating at the 2 quadrant. Now, you have your battery inverter which is operating at the 4 quadrant, because your active power also can be of positive and the negative, your reactive power also can be of positive and the negative. So, depending upon that how much power you are charging or discharging and your rating of your inverters, you can manage the reactive power output from your inverters, battery inverters, and that reactive power output is always maintained below a maximum power limit. Now, how this maximum power reactive power limit is decided? IEEE standard 15472018 is designed to limit this Q max value. That means, you cannot set this value arbitrarily. What it says? It says that for any kind of PV inverter, or you have your grid side converter for wind turbines or bidirectional DC-AC converter, if your active power supply from that inverter is lesser than 20% of the inverter rating, then your Q max will be root over of S square minus P square. But if it is greater than 20% of the inverter rating, then your maximum Q support cannot be more than 44% of your inverter rating. So, that is how this Q max you always have to maintain while considering any time if you want to take reactive power support from your PV or battery inverters. So, these are the few battery projects running in India. India has promised in COP29 that it will integrate 47 gigawatt of battery storage by 2032. We have the largest battery plant that is installed in June 2024 by BSES Rajdhani Private Limited in Delhi of 20 megawatt by 40 megawatt hour battery to supply 12,000 households. Then Mitsubishi and Tata Power Delhi Distribution Limited, they also installed a 10 megawatt lithium ion battery at Rohini. Then you have in Gujarat also the Modhera Sun Temple Town Solar PV Park, they have installed a 15 megawatt hour and 6 megawatt of battery panel, and many more projects, small projects are also coming up in India to reduce or to support the renewable energy integration in the distribution network. So, with this I will end today's lecture and we will continue with this modeling part in our next lecture. Thank you.